Okay, so this is a basic review of momentum and impulse. My hope is to make a couple of short videos, pretty much one every day, that you will watch in order to review some things. So this week we're going to be focusing on momentum. At the end of the week we will start reviewing energy, heat, and work. And for the rest of this unit we'll be dealing with figuring out how to tell when you have a problem where you need to use conservation of energy, where do you need to use conservation of momentum, where do you need to use the heat and work equation, and when is it something else, maybe like kinematics. Okay, so momentum is basically how hard it is to stop something. The equation for momentum, P stands for momentum, equals mv. And impulse, on the other hand, which is different, is the change in momentum. Okay, so there are a couple equations that I gave you guys earlier for impulse. So one is J equals m delta v, another is J equals f delta t, and then combining those two, m delta v equals f delta t. So my question for you is, how can you tell, say I give you a problem and I told you this is either a momentum problem or an impulse problem. How could you tell whether you use conservation of momentum or you use impulse? And the answer is really, if they give you force or time, you're using impulse. If they don't, you have to use conservation of momentum, or maybe it's some other type of problem. So the equation for conservation of momentum is, if you add up all the momentum at the beginning, so that's this side of the equation, sigma p naught, remember sigma means take the sum, it has to be equal to all of the momentum at the end. Okay, momentum is only conserved if there are no net outside forces on a system. Okay, so if you look at my glass of water right here, there is no net outside force. It is in equilibrium. Even though the table is pushing it up, gravity is pulling it down, there is no net outside force. Okay, and by system I mean collection of objects. So you could have one object, you could have two objects, you could have three objects, you could have 800 million objects, or a mole of objects. It doesn't matter, as long as you keep track of the motion of each of the objects in your system. Okay, so assuming you have two objects, this is going to be your conservation of momentum equation all written out. So you have the mass of the first object and its initial velocity, the mass of the second object and its initial velocity, and then it equals the mass of the first object at the end plus the mass of the second object times the velocity of that at the end. Okay, so when do you use conservation of momentum? It's true every time there's no outside force on your system. So technically, you could look at my glass of water and you could say, gosh, momentum's conserved. But that's not going to be super useful if you only have one object. Okay, so in order for conservation of momentum to be useful, you need to have at least two objects. They need to interact, and some words that'll help you figure out that it could be useful are collide, explode, crash into each other. Some others are push off. There basically has to be some kind of event in which they interact. Okay, the other thing is, when momentum is conserved, if you were to add up all the individual impulses, they would be equal to 0. So it's not that you will never use impulse when momentum is conserved. Sometimes you will use it even if there's no outside force, but if you were to add up all of the impulses on all of the objects, it would have to be equal to 0. Okay, so today we're just dealing with really simple 1D momentum problems. The process, and I'm going to do an example problem in just a minute, is pretty basic. Because you have this equation, sigma p equal p naught equals sigma p, you're dealing with a before and after situation. So you need to draw a before and after picture. Okay, so that's before and after the two objects or three objects collide or push off of each other. It doesn't matter. Then you need to find all your m's and v's and solve. One thing you need to be careful of, because I saw a lot of people do this on the last test, don't confuse conservation of momentum with conservation of energy. So if you write this equation, sigma p naught equals sigma p, because there's no net outside force, this is your equation. It's m1 v1 naught plus m2 v2 naught, etc. There's no v squared. Okay, so that the v squared would tell you you have kinetic energy. This is just momentum. Okay, so I'm gonna do